All right, let's talk about rocks. Let's start off with the rock cycle diagram out of our reference table. This kind of shows us the processes that uh, the rocks go through in order to turn into other rocks. All right, so for example, if we start out at magma down at the bottom, start out right here at magma, okay? The process that magma can follow is solidification. That's it. Okay, so there's your process arrow right there. All right. Remember, we also said this is known as crystallization. Okay. If you solidify or crystallize magma, you get an igneous rock. So we're at igneous rock now. Once you have an igneous rock, there's lots of different paths it can follow. You can remelt it to magma and make another one. You can subject it to heat and pressure. You can metamorphose it, make a metamorphic rock. Or you can weather and erode it into little pieces called sediments. And then you can deposit those sediments at the bottom of a lake, bury them, compact them, cement them together, and you can create sedimentary rock. All right. All right, so let's say we have a sedimentary rock. Again, you can weather it into smaller pieces and make another sedimentary rock. You can even erode those sediments again into smaller pieces, moving them into different places, and make another rock. Okay. You can melt it in magma to create an igneous rock, or you can subject it to heat and pressure to make a metamorphic rock. If you have a metamorphic rock, you can melt it into magma to create an igneous rock. You can weather and erode it to create sediments, to create a sedimentary rock, or this is the only one that you can directly turn from itself into another metamorphic rock. All right? It doesn't have to go through an intermediary step. All right? So remember, the arrows are the processes that they go through. All right? So let's talk about three types. Of igneous rock, sedimentary rock, and metamorphic rock. All right, so again, real quick, little flow chart. So we got three types. Melting gives us igneous. We've got intrusive and extrusive igneous rocks, also known as plutonic or volcanic. And these make up about 66% of all the rocks on the Earth. Weathering and erosion, sediments, compaction, sedimentation. These are sedimentary. We've got three types. We have detrital, also known as clastic. We have chemical, also known as crystalline or crystalline. And organic, which is bioclastic. And these make up about 8% of all the rocks on the planet. These are surface rocks. Okay? And those formed by extreme heat and pressure. These are metamorphic. We have foliated and non-foliated metamorphic rocks. And these make up about 26% of all the rocks on the planet. All right, so let's break down into individual ones. First type we're going to talk about are igneous rocks. Cooling and solidification. Okay, cooling and solidification, that's what we're looking for. Or you could see crystallization. What happens is we get various size, shape, and composition crystals. They cool, they crystallize, and they meld together to form one rock with all different shapes, sizes, composition crystals all mixed together. All right? We use the kind of the catchphrase intergrown or interlocking crystals. That's what we're looking for. All right? Extrusive or volcanic. Extrusive or volcanic rocks cool quickly on the surface or very near the surface. We get small crystals, or if it cools fast enough, we could get no crystals. Okay? Small crystals are a fine texture, no crystals are a glassy texture. Okay? Basically, we're looking for things that are less than a millimeter in size. A couple other examples. Pumice has air vesicles caused by dissolved gases that were in the lava. And obsidian is glassy. It cooled super quickly. The crystals didn't have time to grow. All right, intrusive. The magma cools slowly deep down inside the earth, right, where it's still hot. So it takes a long time. Could possibly take millions of years for this magma to cool down. All right, we're going to get large crystals a coarse texture, or we could get very large crystals of very coarse texture in the sense of pegmatite, but we don't deal with pegmatite very much. We're looking at things that are greater than a millimeter, right? So 1 to 10 would be coarse, greater than 10 is very coarse, but essentially we're looking for anything that's greater than a millimeter in size. If you can see it fairly well with the naked eye, it's probably a coarse grain rock. Okay? All right, a little example of a granite. Right? You can see the crystals of quartz. You can see the crystals of hornblende. You can see the crystals of feldspar. They're all interlocked or interconnected together, and they make up the one rock granite. All right, our scheme on page 6. Right? You can see that it separates out based on environment of formation. So anything below that blue line, granite, pegmatite, diorite, gabbro, peridotite, dunite, those are intrusive rocks. They have a coarse texture or a very coarse texture. They have large, easily visible crystals. Anything above that line is extrusive. They have small, they're fine, it's glassy, they have really small crystals and it's hard to see them, or they have no crystals at all, and they potentially also could be vesicular. Extrusive rocks are the only ones that can be vesicular, the only ones that can have gas pockets. All right. If you also look down the chart instead of sideways, you can see the composition. General characteristics, anything on the left is considered light color, low density, felsic composition. Anything on the right side is generally considered dark color, high density, mafic composition. And again, the exception to that is obsidian up at the top left, where obsidian is felsic, but it's a dark black color. And then down at the very bottom is the specific mineral composition. And you can see that on the left side, there's mostly lighter colored minerals, potassium feldspar, quartz, plagioclase. There's a little bit of biotite and amphibole, the dark ones, but it's mostly light colored. Whereas if you go over on the right side, you see a lot of plagioclase, gray, white to gray, but there is a lot of pyroxene, biotite, amphibole, olivine, green and blacks. Those rocks tend to be darker in color on the on the right, and that's where that comes from. All right, sedimentary rocks. Generally formed from sediments or organic matter, like dead leaves, or minerals dissolved in water. And generally speaking, we say they'd get deposited in nice horizontal layers on the bottom of bodies of water. Sedimentary rocks tend to form in water environments. They're surface rocks. There's not very many of them on the planet, but they form in water environments. All right? A good indicator in this particular picture is you can see the layers of compacted sediment. Over time, the weight of the sediment above will push down on those layers and compact them together. This is what's called an outcrop. This was underwater at one point, formed those layers of rock, got compacted. Then at some point, some kind of force inside the earth pushed them up above the water level, and they got exposed for us to discover. All right, so the first type of sedimentary rock is called a clastic. A clast is a particle or a fragment. These kind are compacted and cemented together, and we classify them according to the size of their particles. Smallest size would be shale, a little bigger is siltstone, a little bigger is sandstone, and then the two with the largest range and the largest particle size would be your conglomerate, like we see down in the bottom left, and your breccia. They have a mix of large and small particles together. How do we form clastics? Well, again, we have a water environment, a lake. The sediments get deposited, they get washed downstream in rivers, dumped in a lake, get deposited on top of each other, they push down on each other, and over time they get squeezed together and get compressed, and they merge into a rock, what's called lithification. Okay? All right, second type is called chemical sedimentary rock, or crystalline. All right? These are formed by either water evaporating away, leaving the mineral behind, or a saturated solution, the minerals are going to precipitate out. Right? These are monomineralic rocks. So, for example, the chemical sedimentary rock limestone is made out of the mineral calcite. It's essentially 100% calcite. All right? The chemical sedimentary rock salt is made out of the mineral halite, monomineralic, made out of one mineral. All right? And then finally, we have the organic or the bioclastic. These are essentially made from plant or animal matter. Right? Coal is made from dead plants. It's 100% carbon, so it is monomineralic also. But it's basically dead plants that get buried over time and compressed, and they turn into coal eventually. Right? Organic limestone is the same as chemical limestone. It's limestone. It's made out of calcite, but the calcite is in the form of seashells. And these seashells get broken up, and then they get compressed together. So these are actually formed by compaction and cementation, not by precipitation out of seawater. All right. You can see this little picture showing the formation of coal. We have a swampy environment. Plant material gets compressed and turns into peat. And then if we compress it, compact it, squeeze it even more, eventually it'll end up as coal. Bituminous coal is a sedimentary rock. And then if we have some kind of stress placed on it, earthquake stress, tectonic forces, something, it could metamorphose and become what's called anthracite. All right, in our reference table, we've got a stream velocity chart. This essentially shows us how fast the water has to be moving in order to carry a certain diameter particle. Right? For example, if I said to you, what size particles can be carried if a stream is moving at 5 centimeters per second? Well, 5 centimeters per second is right there. We go up until we hit that. Essentially, anything that's 0.1 centimeters or smaller can get carried by a stream at that speed. So you have your, that would be like a large sand particle, and your silt particles, and your clay particles. Okay? Or if I said to you, if I went the other way, and I said, how fast does a stream have to be moving in order to carry a 0.2 centimeter particle? You would go, oh, I read down here, it needs to be moving at 10 centimeters per second. Okay. All right, here's our scheme for sedimentary rock identification. You can see at the top, we have the clastic texture, also known as the inorganic land-derived. Here's our 5 clastic rocks right here. Here's how they're all basically the same material composition. So this is how we separate them. We separate them by size. Right? I just showed you this one. You can see over here, clay particles are less than 0.0004 centimeters. Silt is from 0.0004 up to 0.006. Sand from 0.006 to 0.2, pebbles from 0.2 to 6.4, cobbles from 6.4 to 25.6, and then anything greater than 25.6 centimeters is going to be your boulders. Right? Down here at the bottom, we've got our monomineralics, the crystalline or the bioclastic. Crystalline is also known as chemical. Bioclastic is also known as organic. These are monomineralics, see? And you can see that these top ones, along with one of the limestones, form from either evaporation of water or precipitating out of a solution. And then your organic limestone, your coquina, cemented shell fragments, and your coal, those are bioclastic. They're caused by cementing those particles together, compacting and cementing those particles together. All right, and finally, metamorphic rocks. Igneous, metamorphic, or sedimentary rocks altered by heat and or pressure. Usually we're talking about continental collisions. We're talking about some tectonic forces here. All right, when two continents collide, they put a lot of pressure on those rock layers. And that pressure, along with the heat that's generated, causes the rocks to change. And they turn into metamorphic rocks. This happens to be an example of a nice metamorphic rock. It's a nice. All right, so a couple examples. Okay, shale turns into slate if you cook it and squeeze it. Granite turns into gneiss if you cook it and squeeze it. And don't forget, you can also get gneiss by taking shale right here, turning it into slate, and then keep metamorphosing this slate into phyllite, then schist, and then gneiss eventually also. I should have drawn an arrow from this to this also, because this could eventually turn into this. All right? Limestone, if you metamorphose limestone, you end up with marble. Right? All right, 2 different types of metamorphic rocks, foliated, non-foliated. Right, these are our different textures. All right, foliated metamorphic rocks have mineral crystals that are arranged in layers. Okay, layers. It's either called alignment or banding. All right, this picture shows kind of in the left how they're all kind of random, and then in the middle picture, you have pressure being put on it, And so the ions migrate and separate out by light and dark, by density, so that on the right you end up with this banded texture of light and dark minerals. And if they don't do that, we just call it a non-foliated metamorphic rock. All right, two different types of metamorphism. Regional, this is where we get lots of pressure over a very wide area, usually caused by continental collision. All right, this is a very large scale change in the rock in that area. All right. A little example here, okay, slate is low-grade metamorphism of shale, but if you continue to squeeze those rocks, eventually they'll turn into phyllite, then schist, and then gneiss eventually. Okay. Contact is the second type. This is more in a limited area. This is caused by rocks touching magma, essentially. The heat from the magma cooks the surrounding rock. All right? So for example, if I have a layer of limestone right here, that heat penetrates into that limestone and turns it into marble. Okay? The heat alters the rock. Okay? Contact, touching that magma. All right? All right, this kind of shows some of the conditions where you're going to get that. Notice up top, hydrothermal and contact. Those are really contact. Hydrothermal is hot water. When the rock comes into contact with hot water, it can change it slightly. But the purple and the green, that's more regional. That's deep change over a very large area, high-grade metamorphism caused by a lot of pressure from continental collisions. All right, so finally, again, what we're talking about here with metamorphic rock is recrystallization, not crystallization. We've already crystallized it into a rock. We're changing it into different crystals. So we don't actually melt the rock. Right? But what we do to it is we make a denser rock. We can change the minerals and make new minerals. We can make the minerals align or band, and we can distort the structure so it's got that wavy look to it. They're not flat horizontal layers.